Hello everybody and welcome back to another stream. Today I think this week we're going to be taking a break from OpenGL stuff and we're going to be doing another programming challenge. It's been a little bit since we've last done one of these, so I figured we can do a challenge that will also help us in the future with a game in C++. So as you can tell from the title, we are going to be doing some more Shunting-Yard algorithms. We've already done it a while back in like at the end of 2019 in JavaScript, where we made it into a graphing calculator in the browser. But today we're going to be creating it for different purposes, and we'll see how that works out. So first thing, I'm just going to start the music really quick. Make sure everything else is okay. Alright, we're all good. Alright, so the first thing we're going to do is we're going to talk about what it is, just if you forget, and then we'll go through some pseudocode, an example with paper and pen, and then we will actually go into writing the code. So the Shunting-Yard algorithm itself is just an algorithm to parse infix notation, so that's stuff like this that you would normally see typed out into reverse Polish notation. So I'm going to be saying RPN for that in this video, and they're the same thing. But essentially RPN is a format that can be a lot easier, or more easy, it can be interpreted easier than just infix notation. So this algorithm will do that based on operator precedence and a couple of other factors. So the algorithm itself is just parsing that infix notation into reverse Polish notation. Now you can use this algorithm and apply it to further areas where you can parse the reverse Polish notation list into a tree structure, which you can then store in a program, and then you can evaluate the expression by traversing through that tree, and that's going to involve some recursion. Alright, so let's go through the algorithm right now. So this is a little bit of pseudocode. I got this from Wikipedia. So the first step is while there are tokens to read in this expression. So let's say you're passing in this expression here. So while there are tokens, like a sign, a left parenthesis, this 3, the caret for the exponent, and the negative 2, those are all tokens. So first thing you want to do in each iteration is you want to read the token and identify its type. If it's a number, you're going to push it to something called an operator queue, not to an output queue, not an operator queue. If it's a function, you're going to push it straight to the operator stack. If it's an operator, so your plus, minus, multiplication, division, and exponents, if it's any of those, you're going to iterate through the operator stack. So while the function is at the top of the queue, or the operator's at the top of the queue, or let me make sure I'm doing this right. Hold on. So it's while the function is at the top of the stack, or the operator at the top of the stack has greater precedence, or the operator at the top of the stack has the same precedence and is left associative. If you don't know what the left associative is, it's just this stuff right here. Like it's essentially a bit of transitive property stuff like that. My mouse is glitching still. Alright, whatever. Yeah, so that's that. And if those every time that's true, you're going to pop operators from the stack to the queue. So you're essentially iterating through everything that has more precedence or is the same precedence, and you're putting that in front of it. And then after that, you want to put the current operator to the stack. If it's a left parenthesis, just push it to the stack, and if it's a right parenthesis, you want to pop everything from the stack to the queue until the top of the stack is a left parenthesis. So you want to go in between the two parentheses, and then after that you just want to get rid of that last left parenthesis. And once there are no more tokens to read, you just want to pop all the operators from the stack to the queue. All right, so let's walk through a little example here using this table here. So these are all the tokens. I wrote all of them out here. So you can see that there's the function is a token, the left parentheses, the 3, the numbers, the operators, and the constants as well. Constants will be read specially as well. All right, let me actually just... Okay, so first thing, first token is sign. So sign is a function, so we're just going to push it to the stack. To stack. So the queue will remain empty, and the stack will now have sign in it. Same thing for the left parenthesis. So then in the stack, you now have a left parenthesis in front and then a sign, because in a stack you push to the front, not to the back. That's a vector list. For the 3, it's a number, so you just add to queue. So the queue becomes 3, and then the stack remains the same. For the operator, for the caret, this is an exponent sign. We're essentially going to go through all this, but because the operator at the top of the stack is already a left parenthesis, we're just going to push it to the top. We don't have to iterate through anything. So we're just going to push to stack. The queue is still 3, and now the stack becomes the exponent sign, and then the parenthesis, and then sign. -2 is just add to queue. So the queue now becomes 3 and -2. Notice that the queue is different because it's a list, unlike the stack, which is where you add to the front. And then the stack is the same, so I can just copy that down. The multiplication, we're going to see that since it's an operator, we're going to iterate through the top of this. We're going to go to the top of the stack, and we see that the operator and the caret has more precedence. So it has more precedence. I can actually make this a little... my mouse is freaking out. God damn, my mouse keeps glitching. So since the caret has more precedence, you're going to pop it to the queue. So the queue becomes 3, -2, and then the exponent sign. And then the stack now becomes a multiplication sign. Just auto-correct it. Don't auto-correct it. Undo auto-bullets. Okay. And then the sign. And remember, we don't pop the left parentheses there. Next, we have a 27. That's just add to queue. So the queue now becomes 3, -2, exponent 27, and then the stack remains the same. God damn it, my mouse. I might graduate to yelling profanities at this in a second. All right. With the division sign, we see that the operator, it's an operator, and the thing at the top of the stack, the multiplication sign, has equal precedence, but it's also left associative. The only right associative operator is the exponent and modulus, but we're not going to do that. So that has equal precedence and is LA. I'll just put that for now. We're not going to LA, but I know you wish you could, but all right. So the queue now becomes 3, -2, caret 27, and then we popped the multiplication sign. God, my mouse. Okay. Yeah. So multiplication sign, and then the stack now becomes a division sign, and then the left parenthesis, and then the function sign. 4 is just add to queue. So that just becomes 3, -2, caret 27 times 4, and then the stack remains the exact same. For the next multiplication sign, it's the exact same thing as the division, so it's an operator, and the division sign has equal precedence and is left associative. So the new queue becomes 3, -2, the caret 27 times 4 divided. Is that right? Yeah. And then the stack becomes the multiplication. Stop auto doing it. And then the stuff that we've had there forever. Oh, by the way, if you didn't know, I probably should have said this before, but I'm evaluating this function over here, the sine of 3 to the negative 2 times 27 over 4 times pi, plus 1, which is equivalent to sine of 3 pi over 4, plus 1, which is, if you are small brain and don't know trigonometry, it's 1 over root 2 plus 1, which is 1.707, just if you didn't know. All right, next, pi is a constant, so it's add to q. So it's going to be 3 negative 2 caret 27 times 4 divided pi. And then the stack remains the exact same. Now we have a right parenthesis. So remember, we are going to push operators to the q until we get to a left parenthesis. So RP, so push to q until you get LP. So the q now becomes 3 negative 2 caret 27 times 4 divided by pi, and we're going to push everything up until the left parenthesis, which is just the multiplication. And then we also delete the left parenthesis, and then then we just get a sign at the end. The plus, it's an operator, and so we're essentially going to push the function because there's a function at the top of the q. So the q now becomes 3 negative 2 caret 27 times 4 divided by pi times sine. I can extend this a little bit. And the stack now just becomes the addition sign. The 1 is a constant, so we're just going to add it to q. And this is just going to become, damn it, the q becomes the exact same thing, just with a 1 at the end. And there's still a plus sign, so at the end, we just want to push everything to q. So it becomes the same thing, and then the plus sign at the end, and now the stack is empty. So what you'll see is that this is reverse Polish notation. And you might have picked up on it before, but how is this easier? It looks like more gibberish, but this is actually quite simple. Now, this is a list of tokens. The 3 is a token, like before, and everything else is a token. So by iterating through each token, you're going to see that the 3 becomes a 3, and it has no arguments in front of it because it's just a number. The negative 2 is the same. Now, the exponent sign is a function that takes in 2 arguments, so we're going to call it a binary function. And you'll see that there are 2 constants in front of it. Now, these will essentially become, in that tree that we talked about, the 2 branches of the tree where the exponent is the root node that connects those 2 branches. So you'll read this as 3 negative 2 exponent, and that equates to 3 to the negative 2. And then that gives you a result. And then the 27, so those 2 and the 27, then you multiply those 2 because of the multiplication sign. And then you take the result of that multiplication divided by 4, because you have a 4 and then division. You take the result of that multiplied by pi. And then because sine is a unary function, so it only takes in 1 argument, you're going to just take the result of that multiplication, plug it into sine. You'll get a sine of 3 pi over 4. And then you'll do that, and then you'll get some constant, which is 1 over root 2. And then you'll take the 1 over root 2, the 1, and you'll add them together to get the final result of 1.707. So it is quite intuitive at some point. So this is essentially just sorting stuff based on operator precedence. Okay, let's actually dive into the code now. This might be a frustrating night just because I have limited mouse functions, just because I honestly have 0 clue why. All right, so the first thing we're going to want to do is, oh my god, is our main file. So add new item. Oh, this is making me angry. Main.cpp. In here, we are going to include iostream and we're gonna do int main std cout hello, and we'll say Shunting-Yard, and then return 0. All right, I want to figure out what isn't it F5 to run? Yeah, it's F5 to run. Okay, so I don't have to use my mouse. All right. Now, like the JSON library, we're going to create this entire kind of library in a single .hpp file. So we're going to call this Shunting-Yard.hpp, and we'll include it in the main file, just like that. And let's get started. So in Shunting-Yard, we want to do our macros. So if not defined Shunting-Yard, define Shunting-Yard, and if in here we're going to include a couple of things. We're going to include vector, we're going to include string, include map, and include stack. So stack is the exact same thing that we've been talking about. And then we also want to include cmath. All right, now, like the JSON, we're going to have a namespace to contain all of our utility functions and our classes. So namespace Shunting-Yard. And in there, we're going to get started with just our main functions. So the 3 main functions that I talked about, the infix notation to RPN, then the RPN to a tree, and then the evaluation. So let me just make sure. Yeah, okay. So we're going to have our section for main functions. I'm going to try and document this as much as I can. So parse infix notation into reverse Polish notation Shunting-Yard. In this, we're going to create a Typedef at the top at some point, just because I don't want to type out vector. I just want to make it more apparent of what this actually is. So we're going to Typedef a vector of a string to RPN, and it's just going to be reverse Polish notation, and we pass in const ** EQN, and we'll define that later. Next function will be parse RPN to tree. So we're going to return a node. This will be another class that we'll create. So it's a pointer to a node. So node pointer parse, and we pass in the RPN object. And then the third object will be the evaluation. So evaluate tree, and that will return a double. So double eval, and pass in a node pointer tree. Okay, let's do our Typedefs now. Where's my holy crap, my mouse is going fucking berserk. I don't know what the hell is going on with it. Okay, alright, so let's go to the top of our namespace and let's do our Typedefs here. So we're going to have our RPN. We're going to have our RPN list. So Typedef standard vector of standard string, and we're just going to rename it as RPN. If you don't know what a Typedef is, it just allows us to rename something, some memory type, as something else. So we're just renaming this vector of a string as RPN, just so it's more apparent of what it actually is. Next, we're going to define our Typedefs for a callback to a unary function. So callback to unary function, and we talked about these, so only has one argument, and this will be Typedef double. Now when you want to do a callback to a function, what you do is you do Typedef, the return type, and then in parentheses a asterisk, and then the name of the pointer. So I'm going to say unary func eval, and then the parameters in another set of parentheses. And then the callback to binary function 2 arguments, and this will be typedef double, pass in binary func eval, and this will take in a double x and a double y. All right. Now we're gonna have something. We're gonna have an enum class to store the types of the variables. So types, and these are gonna be the things that we looked at. Oh, what the hell is going on? When we identify the type. Oh, why is my mouse going crazy? So the operator number, that sort of stuff. God damn it. So we're going to say enum class token types. We're going to have operator, constant, function, left parenthesis, right parenthesis, and else for defaults. All right. Now we're going to create our callbacks to utility functions, because we're going to need a lot of utility functions for parsing, essentially, because when we parse a bunch of stuff, it's not going to be efficient to write that code every single time, especially when it gets repetitive. So we're going to have utility function callbacks. We're going to start off with our determine if vector contains values. In this, we're going to use a template. So template, and it's going to be type name t. And the reason I'm using a template is just so that it can be used for anything, not tpy name, type name. In here, we're going to return a boolean, and it's just going to be called contains. It'll take in a standard vector of t, and then the target value that we're looking for. All right. Next is obtain key list. This will be template type name t. So this will obtain the keys from a map. Standard vector. It will return it as a vector. So vector of string keys. Standard map of standard string t, and we just pass in the map. We're also going to want to be able to obtain a combined key list from multiple maps. That we'll see why in a second. So I'm just going to say obtain combined key list. This will also take a template. Standard vector, standard string, and we pass in 2 maps. So standard map, standard string of t, m1, and standard map, standard string t, m2. All right. Now we're gonna have a bunch of other determining methods. So determine if character is number. So bool is number, char c. I'm realizing now that a lot of this stuff is inefficient, but it works now, and I'm not going to worry about it because it's not too inefficient. There's just a little bit of redundancy in the methods. So determine if entire string is number. So bool is number. Pass in a C string there. Next, we want to determine if string only contains numerical characters, and this is where I'm thinking that we can, I don't know what let me see if I can just remove this. Oh, I know why. Because is number determines if it can be a constant as well, and I could probably find a better way to do this, but for now I'm just leaving it. So bool contains numbers. So this is more for numerical digits rather than constants or their natural constants. So contains numbers takes in a C string as well. Next is to get the numerical value of string. So double get numerical val, pass in another C string. I'll just rename, God, why is this not working? Next method is determine if string matches a function key. So bool is function and we pass in a string. Next, determine if function is left associative, and this returns a bool, and it's is left associative, and we pass in standard string there. And then finally, get function precedence. And I'm going to use a short here just because I don't want to use too much memory. So this is get precedence. And this takes in a string as well. And then finally, there's going to be a method to... What's going on with my mouse? God, I think I need to get a new mouse. I don't know what the hell happened. Whatever, alright. Next one is going to be find element from list in the equation starting at index I. So this is going to be return a string, so standard string, find element, pass in the starting index, pass in the equation as a C string, and then pass in the list of the values that we want to test against. So it's going to be a standard vector of standard string list. Okay, so those are utility functions. We will define those in a second. Hold on, why is this? Oh, I know why. Okay, now we're going to define a class already. This will be our function class. This will store values about a of the function of. This will just store the information for our function objects. So function class definition. So we're going to name it func because we are funky. So class func. That was such a dad joke. Oh my god. I'm sorry. That won't happen again. That will not happen again. I'm sorry. All right, we're going to have a bunch of public members. So we're going to have the default constructor will initialize some things, but we'll just leave it empty for now. We're going to have a, let's actually just define our variables first so we can just do the initialization now. So we're going to have two callbacks. So unary func eval u eval and binary func eval b eval, and this will store the callbacks to the functions that pertain to this function. It'll either be one or the other. We're going to have token types type, so this will be operator or function. Short precision or precedence. Let me actually just comment what these are. So unary function evaluation callback. And then the prec is just precedence. We're going to have bool left, so is left associative, and then bool unary is a unary function. Okay. Now we can actually write the constructors and initialize a couple things. So, default constructor takes in nothing, and it initializes the type with token types operator, the precedence with 0, left is true, unary is true, ueval initialized to null pointer, and b eval to null as well. Next we're going to have constructor for unary functions. In here, we are going to take in a couple of parameters. We'll take in our callback, so unary. We're going to take in our callback, so unary function, eval, token types. Type will be set to default as token types function. Short precedence is equal to 0, and bool left is equal to true. I'm setting these values based on the most common, so you'll see how that's helpful in a little bit. So in this we're just going to initialize a parent, or not a parent constructor, or we're going to initialize a private constructor with type, precedence, and left. And we'll actually define this. I need to find my mouse because it's gonna go fucking crazy. Holy crap. Okay, so that constructor that I was talking about is going to be a private constructor, and the reason why is because we don't want it to be able to, we don't want people to construct it using this elsewhere, because it doesn't initialize everything properly. In here we're going to have func. It'll take in token types, type, short, precedence, and bool left, and it will initialize the type to type, precedence to precedence, left to left. Unary will be set to default as true, and then ueval will be set to null pointer. Or we can actually add in a unary parameter there. So unary will be set to unary, and then b eval will be set to b eval. All right, now this unary function constructor will call that private constructor, and it will pass in type, precedence, left, and true, because it is a unary. And then all it has to do is in the constructor body, because we cannot initialize other members if we initialize another constructor. We're just going to say ueval is equal to eval. And then it's practically going to be the same thing for binary functions. So constructor for binary functions. So func, pass in binary func eval, token types, type is equal to token types function by default. Short precedence is equal to 0 by default, and bool left is equal to true by default. And once again, we will call the private constructor, and then we'll pass in type, precedence, left, and false, because it is a binary function. And then because of that, we want to initialize b eval to eval. All right, so that's good stuff there. Oh shit. Alright, now let's get into a bunch of reference. This is going to be the most boring part of this, just because we are literally this is literally going to be data entry. Reference. Alright, in here, we are going to have our unary functions. This will be a standard map of string to func. and it will take in unary functions, and it will just leave it as empty for now. Binary functions is similar. Standard map of standard string func binary functions is equal to an empty map right now. We're going to have a list for the function names. Now, why would we need this? Well, if you remember in our find element method, we pass in a list, and this list will be names, operators, stuff like that. So we will be passing in the names of all of our functions. And the way to do that is we just initialize a vector saying function names, and it's going to be a standard vector of standard string function names is equal to, we're going to use our keys function. So keys, the type is func, and we're going to pass in our two maps. So it's unary functions and binary functions. All right. Next, we're going to have some constants. So constants. In here, we are going to, we'll just do this right now. So standard map of standard string to double constants is equal to, and we're just going to have pi and e for now. So pi will be initialized as, now this is going to seem a bit weird, but there's no like defined pi in, I mean, there's no defined pi macro. So the way we're going to do it is we're going to take the arctangent of 1, which equates to pi over 4, and multiply it by pi over 4. So standard a tan, this is a function in the math namespace, and we're going to pass in 1 and then just multiply it by 4. Now, if you are interested in this, look up what is it? Look up Maclaurin series and power series, because this is arctangent is, computers don't just have magical binary searches to calculate that shit. So they use something called a power series to actually calculate this with a bunch of terms, and it turns out that this infinite sequence that it generates will evaluate at pi over 4, and it's some weird, really cool stuff about factorials and alternating series, stuff like that. So if you're interested, look it up. But for now, we don't need to. If you were wondering about this notation, this is just how you initialize a pair in a map. We've seen this in the JSON stuff. So then we also want to do E, and E will be initialized to standard exponent of 1. So this function exp just takes the natural base, which is E, and once again that's another power series, if you were wondering, and it just raises it to 1, so anything to 1 is itself. Alright, now we also want to have our constant names. So standard vector of standard string constant names is equal to the keys, and it's going to be of type double this time, because we're just going to pass in the map of string to double constants. Alright, now we're going to have a bunch of other lists. We're going to have operators, so standard vector of char operators is equal to a vector, and we're going to do plus, minus, divide by, multiplication, and the exponent sign that we looked at. God, mouse, please work. For God's sakes, mouse. Yo. We also want to have a list for left brackets, so left brackets, just in case people like to be, you know, really unique in their, evoke their special snowflake abilities and use different brackets just to show their massive brains. We're going to say standard vector of char left brackets is equal to the left parenthesis. You don't have to do this. You just have to, if you want, you can just do the single left parenthesis, and that's it. but I'm just going to do it with the left curly brace and the left square brace as well. And then likewise for the right brackets. Standard vector char right brackets. Alright, now let's go ahead and initialize some of our functions. We'll just do a couple because we don't need many. We're only going to do all of the operators and just just 2 unary functions. How about that? Okay. So we'll start with the operators. So operators are binary functions because they take in 2 parameters. Or rather, let's do the unary function first. Let's just do sign for now. So the first one is going to be sign, and sign maps to a function, and we're just going to pass in the callback to it, which is just standard sign, and that's it. Now this is the reason why I put in all those default parameters, because sign conforms to, conforms to a precedence of 0 because functions don't have precedence. The type is function and it is a left associative function. So yeah, that's why I'm doing that there. God damn it. Alright, so that's the only... Oh, this mouse is... I might just throw this mouse through the window before the end of the stream. I don't know. Alright. Now let's go into our binary functions and do our operators. So let's start with the addition sign. This will map to a function, and now we're going to use something called a lambda function that allows us to initialize or create a callback within a single line. So all you have to say is, for a lambda, you just put 2 square braces, put the parameters in parentheses, so double x and double y, put the arrow, so a dash and then the greater than symbol, and then the return type double, and then in curly braces put the body. So all it's going to be is return x plus y, and we can do that in a single line. Now this will also take in a different parameter because it's not a function, it's an operator. So pass in token types operator, and it takes a precedence of 2. Alright, you can actually... God, I'm gonna go actually berserk if this mouse doesn't stop fucking up. 4, 5. Alright, I'm just gonna do that 5 times. So we have the subtraction, multiplication, division, and well, I don't even know what's called, the frickin' power symbol. Hold on a second. Alright, we're all good. Alright, so for subtraction, just update it to minus y. Multiplication is times y. Division is divided by y, and then the well, actually, what we can do for the power is we can just pass in a callback to standard pow. There we go, that works. Because the pow takes in 2 parameters, x and y. It's an operator, and it has a precedence of 4, and it is not left associated, so we have to pow. False, that's all. And then update the precedence on the multiplication and division to 3. And that's all we need for binary functions for right now. So we can minimize those, minimize our constants, and that is good for our reference. Now we are going to go ahead and do our node classes. So below reference, let's go ahead and do node class definitions. So in node, we are going to have a base class that will give us the base properties of a node, so its branches and then a couple of values. And then it will also provide a template for an evaluation function. So base node class, class node, and it only has public members. It's going to have a constructor that takes in a name as a string, and Boolean is function. And it will initialize name to name, and we'll do this in a second, and is func to is func. So for those members, we're going to have standard string and bool is func. And then, like I said, we're going to have an evaluation method, so double eval, and this will take in two parameters. Double x is equal to 0 by default, and double y is equal to 0 by default. Next, this is gonna, if this malv, it's getting really close just to going straight out the fucking window. Alright, now for the children of this, it's gonna have pointers to other nodes. So node pointer right and node pointer left. I'm gonna turn this down a little bit. Alright, so that's our base node class. Now for our inherited classes, we're gonna have a function node class and a number node class. I'm playing Pac-Man and I can't do it. What did I just open? No, I don't want you, Microsoft. Alright, for the function node class, we're going to say class func node inherits from public node, and it has public members. So it takes in the default, or in the constructor, we're going to pass in a name, so standard string name. And this will initialize a parent class of node with name and true because it is a function, an empty body. And then we're going to want to have a function to set a type of function and then assign callback. So this is going to be set void set unary, and it will take in a parameter boolean for is unary. For now, it's going to say this. Or not for now, it's going to say this is unary is equal to is unary, and this is going to be a member that we will declare. Let's actually do that now. So we're going to say bool is unary, and then we're also going to store a function object here. So func, and this is the class that we initialized or created. And then in here, we're going to say if is unary, this func, or we can do a ternary operator. So this func is equal to is unary, unary functions at name, or binary functions at name. So if it is unary, take the value from the unary function, otherwise take the value from the binary functions. And then for evaluation, what we're going to say is evaluate, so return double eval, and it will take in double x and double y, which is equal to 0 by default, because for unary functions we only take in one value. So for eval, we're going to say return this func dot evaluate. Did I create that method? X and y. I did. Okay. No, not b eval. Did I not do that? Hold on, I may have forgotten something. Yes, I did. Okay. So in the function class, we forgot to do our evaluation function. So double eval, taking double x and double y. And in here, we're going to say return this a ternary operator. So this unary. So if it is unary, evaluate the unary function with just x, and then otherwise evaluate the binary function with x and y. And that should fix every. Oh, I'm getting angry. Stupid fucking mouse. Alright, so that should be it for the function node class. Now let's do the number node class. All right, number node class. We're going to say class num node inherits from public node. Public members only. Constructor takes in a name, so num node, numnuts, standard string name. Initialize our base class of node with name and false because it is not a function, and empty body, and then return numerical value. We're gonna have a function for that, and there's gonna be double eval, and all it's gonna take in our two default parameters just so it's evident that it is inheriting from the node class, and we're gonna say return get numerical value, and we're just going to get the numerical value of the numbers, so name.cstring, just like that. All right, and those are our node classes. Now we can actually go into creating our, or let's do our utility functions first. I'll blue ball you boys for a little more. Let's just copy all of the utility functions, all the callbacks, and paste them down below, and make this utility functions definitions. All right, let's start with contains. Oh, this mouse is making me angry. So for contains, we're going to return standard find from v.begin to v.end, and we want to find the value x, and if that is not equal to v.end, return true, otherwise return false. For keys, we are going to say we're going to have our placeholder for return, so standard vector of standard string ret, and we'll return ret at the end, and we're going to say push each key from each pair. So for auto const reference element in M, so this is going to be for each pair. We're going to say ret.pushback element.first, because essentially a map is a list of pairs, and the first element in a pair is the key in a dictionary. Now for the combined key list, what we're going to say is we're going to have we're going to get keys from each map, so standard vector of standard string key set 1 is equal to keys, pass in the type t, and pass in m1, we're just calling the function above. Next, standard vector standard string key set 2 is equal to keys, and we pass in m2 this time. We're going to insert the second list into first, so we're going to say key set 1 dot insert from the end of 1, so key set 1 dot end, and we're going to go from key set 2 dot begin to key set 2 dot end, and then we're just going to return result. So return key set 1. Okay. We have a couple more. Hang in there. This is going to be very annoying. All right, 4 is number. What we are going to say is we're going to do one big thing. So return either C is equal to a decimal place, or the code value matches some predefined things. So if the integer value of C is greater than or equal to the integer value of the character 0, and the integer value of C is less than or equal to the integer value of 9, so any of the 9 digits, or C is equal to the negative sign. And this will cause complications with subtraction signs, so we will have to determine when it is and when it isn't. Now, for isNumber, we are going to say return. We're going to see if it's either a constant, if the first character is a decimal place, or if it only contains numbers. So if return contains standard string, pass in constant names and C, or string std string compare C and the decimal place is equal to 0, or not C, str, my fault, or contains numbers str. Alright, now for contains numbers, we're essentially going to try and prove that it doesn't. So the way we're going to do that is we're going to try to prove wrong, either not a decimal, so we're just going to try and prove wrong. So in here we're just going to say for character C in standard string of str, and if is number C, so if it's not a number, if not is number C, then just return false. And after that, we have not proved it wrong, so return true outside of the for loop. For get numerical value, we're going to use a couple of things here. So if contains standard string constant name, so if it's a constant, we're going to return constant at string, so return the numerical value of it. Otherwise, return standard A to F, that's string to double of string. Alright, four more. For is function, we're just going to say return contains standard string, pass in function names and C. For is left associative, we're going to say return binary functions at c.left. Now the reason why we're only doing binary functions, or at string rather, is because all of the unary functions are left associative, so it is pointless to so we won't be testing for that in the code, but we will for binary functions. This test will only apply to binary functions. For get precedence, we're going to say if contains standard string keys of binary functions and C and string. So once again, this is a function that only applies for binary functions, because the precedence for all the unary functions is all 0, because those are just pure functions. So it's going to return binary functions at str.precedence, and otherwise just return 0. There we go. All right, last one, find element. So this is a little, this is a really helpful one. All it's going to do is say for standard string item in list, we're going to say int n is equal to the size of the item, so the size of the target item, or of the current item that we're iterating through, so integer of item.size. And we're going to say if standard string of equation dot substring from I to a size of n is equal to item. So essentially the substring from I to I plus n, if that matches the function, we are going to return the item, and otherwise we're going to return a blank string. So this does come in dandy. What the hell is going on? My computer's all bugged out. I don't know why, but I'm getting like a static. I don't know if you guys can see that, but there's like a static thing in that volume. Whatever. I hope it's going through. Oof. That would be kind of funny if it wasn't. Alright, 1 hour mark and we have not done the algorithm at all. Wonderful. Alright, I hope this doesn't take too much longer. Alright, so let's start with the actual algorithm's functions. Or let's delay it even more and let's just do our let me just find this real quick. Well, let's set up the main file. So we're going to take an equation from input, so standard cout input equation, and we don't want to end a line. We're going to get the equation itself, so standard string eqn, standard get line. We're going to pass in the in stream, so standard cin, and eqn to store it, and then we're going to say standard vector of standard string rpn is equal to Shunting-Yard reverse Polish notation, and we pass in the C string of eqn. Next we're going to say Shunting-Yard node pointer tree is equal to, we're using our namespaces here, so Shunting-Yard parse rpn. And then finally, we are going to output the value of it. So standard cout, the equal sign, and then just print out Shunting-Yard eval, and we pass in the tree. All right, perfect. So there are essentially 3 steps to all this, but once again, this evaluation can be changed or can be reused since the tree is stored in memory using the node class. Sorry, let's get started with the actual algorithm. All right, let's start. First, we're going to need our queue and our stack. So standard vector of standard string queue and standard stack of standard string stack. So I'm essentially going right through, where's my mouse? Oh God. There it is. I'm going right through all of this stuff. I'm following this exact format, having a queue and a stack. All right, so we're gonna need a placeholder for our object. So standard string object is equal to something empty. We're gonna have a type, so token types type is equal to token types else for now, and then we're gonna store the previous type, and this will come into play when we want to determine if the negative sign is actually a negative sign or if it's a subtraction sign. So token types previous type is equal to else as well. All right, now let's go through each character in the equation. So for int I is equal to 0, eqlen is equal to int of the string length of eqn, I is less than eqlen, then I plus plus. I'm not saying len, don't worry, it's not that. All right, so first thing we're gonna want to do is we're gonna want to get the current character. If my mouse would move. So char t is equal to eqn at I. We're going to skip spaces and commas. I don't know why we would need commas, but they have come up. So if t is equal to an empty space or a comma, so if t... So if it's either of those, we're going to set the previous type to else and continue, because we don't want to do anything for it. Now we are going to classify token based on the first character. So if is number t. So there are several possibilities here. If it is a number, we're going to initially set it to constant. So type is equal to token types constant. So if it is a number, we're going to want to get each numerical character after that until there are no more numerical characters. Oh, this might be... Alright, well, let's just do it. So, int start I is equal to I. If I is less than eq len minus 1, so before we get to the end of the string, we're going to want to say while is number eqn at I plus 1, and that's why we have that offset of 1 at the end. We're going to say I plus plus. And then we are going to say after this is if I is greater than or equal to eq len minus 1. No, we actually, yeah, I was getting errors, or we'll leave it up. No, never mind, I'm not taking a chance. I was getting errors with this, without having this in testing, so I'm just going to have this, just going to leave it in for now. So if that is true, then break. What is the... Oh, yeah, I put square brackets here, that's why. Alright, now, after that, we're going to want to say object is equal to standard string eqn dot substring from start I to I minus start I plus 1. That, once again, just trial and error. Okay, now, for the subtraction sign detection. So if the object is equal to a negative sign and that alone, we are going to say and the previous type is not equal to a right parenthesis, so token types are paren, and the previous type is not equal to an operator, so token types operator. We know that this is a subtraction sign, and once again, this is a lot of trial and error, and also just logic, because if the previous thing was an operator, then it can't be two negative signs in a row, or then it can't be two subtraction signs in a row, so it is a negative sign. But if it isn't an operator, then it is an operator. Well, if the previous one wasn't an operator, then this is an operator. So type is equal to token types operator. Alright, now if it is not a number or not classified as a number, we're going to use our find element functions, find element function several times. So we're going to say object is equal to find element. Let me just scroll down a bit. Find element. We're going to pass an I equation and the list. So we're going to say function names. If object does not equal an empty string, that means that it found something. So type is equal to contains char, operators, and object at 0. So if it is an operator, we're going to say the type is token types operator. Otherwise, it is a function. So token types function, and that's that. Now, if the object was something blank, that means that it didn't find a function. So else, we're going to say object is equal to find element, and this time we're going to test for constants. So I, eqn, and constant names. So if object does not equal a empty string, once again, found valid object. So type is equal to token types constant, and that's all it can be. Why am I getting errors here? Oh, I misnamed this. What is this? I'll have to figure that out later. Okay. So once again, if it did not find a valid object, we're going to then assume that it is either a parenthesis or something that is not valid. So else if contains char left brackets t, type is equal to token types L paren, and object we'll just set to the left parenthesis as default. And else if contains char right brackets t, the type is equal to token types R paren, and object is equal to the right parenthesis. And otherwise didn't find anything. So type is equal to token types else. Now, after all that, those if statements, we're going to want, oh, come on. We're going to want to add the size of the object. So I plus equals object.size minus 1. So this was token reading and detection. I'm going to grab a glass of water and I'll be right back. I am returned. Alright. Let me just X out of a couple things here. Alright, so we are about halfway through the soundtrack. Nice. Alright, now let's actually write the bulk of the algorithm. Now I just exited out of OneNote, but essentially we're going to translate all that pseudocode into something here. Alright, so after all, what's going on? Oh my god, this mouse. Alright, after we determine what the token is, we want to do something with the token. So the first thing we're going to do is we're going to get the C string of the last stack, so last item on the stack. And this is equal to, and we're going to use a ternary operator here. We're going to say, so if stack dot size is greater than 0, and if it is, we're going to get the stack dot top dot c. Oh, if it is, we're going to get the stack dot top dot c string. And otherwise, we're just going to use an empty string for now. All right. Now we're going to get a switch over the types that of the type that we identified this token to be. So the first one we're going to have is case token types constant. This is another reason why I use an enum class. It's super easy to put it into a switch. So if it's a constant, we're just going to push it back to the queue. So queue.pushback object, and then break. Next, case token types function. That's just stack.push object, and then break. Next is case token types operator. And in here, we're going to say if stack.size it does not equal 0, and if it is equal to 0, we're just gonna, or at the end of it all, we're just gonna push the object to the stack. Remember that from the pseudocode. But if there is stuff in the stack, we're going to use that really long while loop with a bunch of conditions. So while, and in this while, we are going to have a couple of things here. So write this code exactly as I do. Like the notation here needs to be exact and precise because the conditions need to match. So if open two sets of parentheses and say contains standard string functions last stack and does not contain char operators last stack at 0. So this just means that function names rather. So all this means is that if there's a function at the top, but it's not an operator, so that's that. Or we're going to say get precedence of last stack is greater than get precedence of object, or if get precedence of last stack is equal to get precedence of object, that condition, make sure that this is now open two sets of parentheses and put the that last one in there, and then if the precedences are equal and is left associative last stack. Alright, I hope my parentheses match up. So we have, yeah, that works. Alright, there. And then this all and it's not a left bracket, so it does not contain char left brackets last stack at 0. Let me actually just organize this a little better. So yeah, this is just the bunch of the code that we wrote. This is very messy, but don't worry, it's fine. It works, that's all. So simple enough in the loop, we're just going to say q.pushback stack.top. And then we're going to say stack.pop. So once we get the top object, we're going to pop it. And then if stack.size is equal to 0, we're just going to break. And then after this, we want to say last stack, and we want to reset it so it's equal to stack.top.cstring. All right, well, we took care of the pushing. All right, now for next case, we have case token types l_paren, and if it is, we just stack.push object. Or, you know what, I screwed up. When we do this here, we don't need to set the object to the left parenthesis, because we can just pass in stack.push left parenthesis there, and then break. Now for a right parenthesis, so case token types r_paren, we're going to say while last stack at 0 does not equal a left parenthesis, or make sure that's a character. Or you can just say while last stack does not equal a left parenthesis. We're going to say q.pushback stack.top. And then stack.pop once again. So we take the top element and then pop it off, and then reset the last stack. So last stack is equal to stack.top.cstring. And we don't need to check to see if the stack size is 0 because we know that we're looking for a left parenthesis, and if it does, that's the user's error, so that's their fault. And then after this, we want to pop the left parenthesis that we know is at the top. So break. All right, so those are all of the conditions, all the types, and then default. So if it's else, we just want to return the Q. And then after each iteration of the loop, we want to reset the type. So prev type is equal to type, and that's that. Now, after this, what we want to do is we want to take everything that is still on the stack and put it to the queue. So while stack.size is greater than 0, q.pushback stack.top, and then stack.pop. All right. And then after this, we just want to return the queue at the end. Perfect. Now, we can actually just return null pointer for now, just so we make sure that this all works. So return 0.0. So in main.cpp, let's go ahead and add a breakpoint after the. We can actually change this type to Shunting-Yard RPN, just like that. All right. So let's go ahead and run this, and we'll in x64, just because we'll probably be using it in an x64 context, but it doesn't matter too much. So let's do our equation. So let me actually just open up OneNote again. All right. So let's input this equation here, and I'm just going to copy and paste it as infix notation. I'm going to paste it in there, and we stopped at the breakpoint, which what is going on? Oh, there's an infinite loop somewhere. Oh crap. Alright, where is this infinite loop? Where did I forget to put a break statement? Let me put a breakpoint right after the loop, just so I make sure that we're getting all the objects properly. What? Why am I not getting objects? All right, well, give me 2 seconds here. No. I don't want this last stack, I want the object. Does it have something to do with this? Hold on. Now, let me just stop this real quick. Oh, okay. I'm just gonna put that there and just as a placeholder, just so I can make a breakpoint there. Alright, why am I not getting the... Why am I not getting the object in the thing? I should be getting an object right here, but it's... Oh my god, there's something wrong with the code. Alright, let me walk through this line by line. Oh, great. Wonderful. So, QStack, object, type, previous type. I is equal to 0. EQ len is equal to the integer of the string length of the equation. I is less than EQ len, I plus plus. T is there. Let me just make sure that it's getting a right length for the equation. EQ len is 27, that looks about right. Alright. Now, skip our spaces and commas, yep. Classify the tokens. So if is number, set the type to constant, and start I is less than EQ len. I feel like it would have to be in here. I really do. Alright, let me just do this real quick. What just happened? Oh, I'm an idiot. I got rid of the... Oh my god, my mouse, please work. Oh my god. Alright, so let's do this. What just happened? Oh, it never finds a number. Alright, let's figure this out. What? So... Alright, we're going to start simple. Sine of pi divided by 2. Should get 1. Alright, the token is S, that's right. That should not be a number either. Oh, I know why, because it's getting stuck on the left parenthesis. That's why. Because okay, I see now. So we do need to set the objects to the left and right parentheses if we detect it. That is a must. And then what we can do is just say yeah, okay. Alright, so that makes a little more sense. Alright, let's get rid of that breakpoint, and hopefully everything else works out. Uh-oh, my mouse. Oh, okay, this mouse is going straight out the window right after this, I swear to God. Holy crap. I feel like I've seen this before. This error. Empty DQ. Now let me just make sure that it's identifying a type right. So let's just print out the all right, let's just, oh god damn it. This is purely debugging. Alright, so object assign, type function, good. Left parenthesis, constant, operator, yeah, that's good. Constant, operator, constant, and then the division sign operator, constant, yep, right parenthesis, and ooh. So it's after the right, okay, so there's something about a right parenthesis here. That's wrong, alright, so let me check my code. Oh, it might have to be this. So while last stack at 0 does not equal the character. I don't know why that would change anything, but that probably works for some reason. There we go. Okay, so let's now put a breakpoint and see what we have as our reverse Polish notation list. Alright, so for our equation, that's what we got. And now for RPN, let's see what we have. We have a 3. Here, let's compare it with this real quick. So at the end, we should get this stuff right here. So we have this is what we should get. So we have a 3, -2, caret 27 multiplication of 4 divided by pi times sine 1 plus. Perfect. So yeah. So that is all working properly now. That is good. Alright, so now let's actually write our other functions that will allow us to evaluate this several different times. Alright, let's start with the parse to a tree. So in node parse, we're going to have a stack. So standard stack of node pointers stack. And then at the end, we're going to return stack.top. Now this is technically the second part of this algorithm, but not really, because we are essentially using the reverse Polish notation in a different way, because usually it's used just to evaluate it on the spot, but here we want to store it. So we're going to say for standard string item in RPN, we're going to say if is number item.cstring. So if it is a number, we're going to push number node. So stack.push new num node, and we're going to pass in just the name. Now the reason why we can do this is because we'll see what the difference is with the function. So otherwise it's a function. It's a function. So we're going to say func node f is equal to new func node, and we pass an item as the title. Alright, so now we want to determine the type of the function, so binary or unary. So we're going to say if contains, make sure that's func node, not note. So if contains standard string, the keys of binary functions in the item, we're gonna want to say so we now, I swear to God, we're gonna set the unary to false. So f set unary false. And And then we're also going to assign the children of this. So set children of node. I wish I had my drawing pad with me, or my drawing tablet, because I would be able to diagram this. So f right is equal to stack.top, and then stack.pop. The reason why we're doing the right node first is because with the exponents, you see that the -2 does not come first. The 3 comes first. So we want to go left to right. So we're going to say the left node is the base and the right node is the exponent here. So stack.pop, and then we're going to say the same thing for the left. So f left is equal to stack.top. And this is now the second top because we have popped the right node. And we're going to say stack.pop. And this is all going to look pretty recursive, I'd say. Because, let me just make sure. Yeah, well, no, it's not recursive, but the thing is, we're essentially going through, I did a diagram on this in the last Shunting-Yard challenge, but there it looks a little more formal, but this, you can kind of get the gist of it, because I talked to you about how if it's a binary function, it's going to have 2 numerical arguments in front of it, and otherwise it's only going to have 1. And that's just based on how we minimize it. And so essentially what will happen in the evaluation is this 3, -2, that will become some number, 3 to the -2. And then that, so let's just actually take this and we'll see how it works. So evaluation. So let's just walk through this. So we start with that, and then so next step is 3 to the -2. What is that? 1/9. So 0.1111. Yeah, so 0.111. Repeating. 27 times ... Now the 0.111 27 times, that's going to give us a 3. 3, 4, no. Oh yeah, 3, 4 divided by ... This is going to give us a 3/4. So 0.75 pi times ... This is going to give us a 0.75 times pi, which is I'll just put it as 0.75 pi, and then we're going to have a sine ... So then sine of 3 pi over 4 is going to be 1/√2, so 0.707, 1 plus, and this gives us 1.707. So essentially we're working our way through the list, and we're going to create a stack, another stack essentially. Unary function, so or binary function, it has 2 arguments. Else if contains standard string keys, unary functions, and the item. So if it does, it's going to be a unary function. So f set unary true, and then we're just going to say set child of node. So f left is equal to stack.top, and then stack.pop, and then once again, because this is because we want to continue with this result here, we're going to say stack.push f. We want to push the node back onto the stack once we've taken care of it. And after this, we want to say if after the loop, if there's nothing left on the stack, so if stack.size is equal to 0, we just want to return null pointer. I put square brackets again. All right, just like that. And then after that, we want to return the top. All right, so now let's do the evaluation. And this is going to be tree traversal. So essentially all it's going to be is, this is going to be a recursion. So we're going to say if tree is func, so if it's a function, or let's just do the numbers first actually. So if it's not a function, so a number node. So we're going to say return I should be able. Let's just say we're gonna say tree eval, and remember with a number, or eval with nothing in it, because if it's a number, the default arguments are 0 and 0. Okay. However, for function nodes, we're gonna have to convert it to a function node itself because we need the unary property. So func node pointer f tree is equal to func node pointer of tree, and we're going to say if f tree func.unary. So if it is unary, isn't there a thing for that? Is unary, yeah. We're going to say return f tree eval, and because it's only one argument, we're going to pass in the evaluation of the left node. So tree left, and then 0 is automatic for the second parameter. And otherwise, we're going to pass in both children, and we're going to say return f tree eval, and we're going to pass in the left side, so eval tree left, and then eval tree right, and this will all go back to a number where this recursion will end. So that's going to be that there. So let's run this out and let's see how it works. Yeah. All right. So let's go ahead and get the infix notation here. Build errors. Okay. Oh yeah. Yeah, I never. Okay. Yeah, that's why. So we do need to convert this to a number tree. So node tree eval. So essentially just convert the tree to a number node if it's a number, just because we need that, because that eval function is not defined for a base node. So we're going to say here, input equation, paste the that, read access violation. Oh, once again, I didn't change it. Okay. So make sure that this in function evaluate, or in func node evaluate, make sure that it's this func eval, not b eval. It auto corrected for some reason. Yeah. All right, paste it in. Aha, good. So that is pretty cool, right? 1.707. That was our desired result. Pretty cool. I'm enjoying this. All right, now last thing I want to do is variables. So if I can find my mouse, I need to figure out how I want to do this. So you're not only going to have constants all the time, we're sometimes going to have variables as well. So this is going to go under our reference as well. So we're just going to have a variables. So standard map of standard string to double variables. And we're not going to have a vector of the string of the variable names because we can add or subtract variables. So it's going to update every time during each evaluation. So essentially, we're going to have to add a couple of extra statements here. So in when we parse it to reverse Polish notation, it's not going to figure it out as a number because x or y, those aren't constants, those aren't pi, that's not e, it's not a number. So what we want to do is in the else statement, so if it's not a number, and if it's not a function, because the functions will have higher priority, in that first, and then after the constants, we want to do pretty much the exact same thing. So in the else body of the constant, so we're going to say object is equal to find element I eqn, and we're going to pass in the key list. So keys, double, and variables. So this gets us an updated variable list. And then we're going to say if object does not equal something blank, we're going to say type is equal to token types constant. And otherwise, we're just going to put an else if there. Damn, we have been going along for a while. Holy crap. We're almost done with the Hyperlight Drifter soundtrack. So this has been a bit. It's been a minute. Alright, and apart from that, we are going to handle it in the exact same way with the stack as we would a regular number, because it essentially is a constant at the time of evaluation. Alright, so next thing I want to change is in the number node class. So go up to our no. Hold on, let me just make sure I'm doing this right. Yes, okay. So don't go to the number node. Go down to our utility function definitions. Go to is number. So the which one is it? The second one. So bool is number that takes in a C string. So we're going to say if contains constant names or contains standard string keys double of variable names, variables, and string, or so a number can also be a variable name. And then finally, what we want to say is in get numerical value, we want to add another else statement. So else if contains standard string keys doubles or double pass in variables and C. So if that is true, return the variable value of C. str rather, not C. str. And let's go ahead and actually try this out. So go into main and let's say this time Shunting-Yard variables at, let's say x is equal to 15. Let's just do x, and then we get 15 there. Now let's put it in an expression to make sure that it handles it like a constant. So x x squared divided by 5 plus x. We should get 225 divided by 5, which is 45 plus 15, 60. Oh my god, the big brains. Oh Jesus, the big brains. Alright, it works. Beautiful. We're done. This has been going on too long. I'm pulling my hair out. Oh my god. Yeah, that's pretty much it. Code will be on in a second, on GitHub rather, and I'll probably put it into its own repository so it can be a library. And then in the next, probably later this week, I will stream again on Thursday, because that's when my schedule becomes Tuesday and Thursday. I'm planning on either playing some more Minecraft because I have a project to do for school. I know. Or I'm going to do some OpenGL where I want to fix those image errors that we ran into last time. And then I want to create a video on how to use this Shunting-Yard algorithm to create some functions that we can use in our real world physics world, in our application. And so that's stuff like transitions and physics, stuff like that. So yeah, that's been a long stream. Jesus Christ. Yeah, that's about it. I will see you guys then. Bye.